Okay, let's look at the definition of a derivative a little more closely. We're going to look at secant slope, and then we're going to look at tangent slope. So in this video, we'll be looking at defining the derivative at a point. Later, we'll be talking about defining the derivative as a function in the next step. So the point in question is going to be like the x value is going to be c. So the first thing I want to do is I want to zoom in on this graph, and I want to go ahead and plot that point c like that. There's the point when x equals c. Now, for a secant line, we need another point. And that other point is going to have another x value. Now, the way I want to set this up, I'm going to talk about the distance between these 2 points. We're going to call that either delta x or h. Same thing. Some textbooks use delta x, others use h. H is a little easier to write and say. So most of the time, I'm going to be using h. That would make this point here c plus h. H can be a negative number, so the c plus h can be to the left of c. That's possible, but I've drawn it to the right. Now, having done that, now the line connecting these 2 points here is our secant line. Here, secant. And its slope, secant slope here would be calculated by change in y divided by change in x, rise over run. Yeah. And I would calculate this by using the function values. So our denominator is going to be just h. Let's make that a little bit bigger. Come on. Yeah, our denominator is going to be just h. But our numerator is going to be the change in y coordinate, which we can you think of it as like y2 minus y1, but we can write that in terms of function outputs. F of c plus h, that'll be this y coordinate right here, minus f of c, which would be this y coordinate over here. So so there's that right there. I'm going to put a box around that. That thing is the expression, the algebraic expression in terms of a function that calculates the slope of a secant line for that function between the point c and c plus h. Right here I wrote c to x. We could call that x c plus h. I wrote x. I'll explain why I wrote x in a couple of minutes. This expression has a name. You'll actually see this referred to as a difference quotient. Difference because the numerator is a difference. It's the difference in y values. The denominator is also a difference, despite the fact that there's no subtraction in the denominator. H is a difference. Difference between these 2 points. Okay, difference as in subtracting. It's also a distance. And then it's a quotient. Quotient means divide. Right? It's like the result of division. This is called an example of a difference quotient. Now, if we want to define the derivative is really what's going on in this second one down here. The derivative is going to be down here. So we'll have our point C again. There. This time, instead of a secant line, we're going to be aiming for a tangent line. So I'm going to draw the h a little bit smaller. Here's our c plus h point. And we're going to imagine that this point is approaching c. And the way that we do that is to take a limit as h approaches 0, or delta x approaches 0. Okay, so the derivative is going to be called the derivative of f of x at c, and it can be written as the limit of the secant slope, the limit of the rate of change, limit of the slope, delta y over delta x, as delta x approaches 0. Or equivalently, the limit as h approaches 0 of this difference quotient we wrote up above. Okay, so we have the difference quotient up here, which tells us the secant slope, and then we have the limit of the difference quotient down here, which tells us the tangent slope. This is just a rate of change, average rate of change in the function. This is an instantaneous rate of change. And this one down here is called the derivative. And there's a special notation, which is to put up what's called a prime on the f. When you type it, it's just the apostrophe, but it's like a little tick mark above the f. And that means derivative of f. At least that's one possible notation for derivative of f. And then since this is at c, we put a c inside here, taking the place of where the f would be. So this is also called f prime of c. Okay. Okay, so this is how we define the derivative. I'm going to show you an example soon of how you can actually calculate it using the limit strategies we learned in the previous unit. But before I do that, I want to also write on this page an alternate notation that you will see. You've seen it in previous videos, perhaps. Instead of calling this c plus h, we could be calling it x, right? I said it there, it's from c to x. And so this here, this could be called x instead. And then we could write this in terms of the c and the x. So this could be f of x minus f of c. And then in the denominator, instead of using h is going to be the change in x, which is the x minus the c. So this is an alternate form. It's still called the difference quotient, just an alternate form of the difference quotient. We can do the alternate form down here as well. F of x minus f of c all over x minus c. Now, in the original form, the variable is h, right? Like in the original form, h is the variable. H is the thing that's approaching 0. In the alternate form, x is the variable, but x doesn't approach 0. Let's look back over here. If this is x, what is x doing? X is approaching c, okay? So when we set up the difference quotient, the limit of the difference quotient for the derivative, in the alternate form, we have the limit as x approaches c. Now, you might be wondering, why is that one the alternate form? Why isn't that the main one? In fact, actually, most times that I've talked about tangent lines until now, I have been using the alternate form. So why is that alternate? Why do we prefer the version that involves the h, c plus h? The reason is because when we want to generalize this idea of derivative at a point to the derivative at a variable point, and therefore like viewing the derivative as a function of x, we don't want to have another x floating around in our definition. So we're going to use x in place of c, and we can't have x and then x again and have them mean different things. So just in terms of like ease of communication, in terms of ease of of notation, it is better to use the c plus h version, because then later we can make that x plus h, and it just works out more cleanly. Plus, you can standardize the format so that the limit is always as the variable approaches 0, as opposed to having to have that limit approach some other variable, like if x1 approaches x2 and they're both variables. Yeah, the version in blue on this page just works better when we generalize to functions. So in the next video, I'm going to do an example.